So welcome to webinar 4. This is all about pedagogical approaches in computing science. So this session we're going to look at 3 such approaches. So we're not talking so much tonight around the kind of subject knowledge of working with Scratch or computational thinking, but actually how we teach this stuff, not what we teach, but how. I'm going to introduce 3 different pedagogical approaches. First one called PRIM, then use, modify, create, and Parson's problems. Of the 3, I use Parson's problems all of the time in my teaching at school. I also use PRIM occasionally for more in-depth, longer series of lessons. In fact, I use them all because I do use, modify, create, as we did last time we met when I was providing you with some code for the Camel dance routine and you sort of worked with that. So these are ways of working to deliver your computing science lessons. So let's get straight into it then with the first one, which is called PRIM. So there's a bit of information about PRIM on the Barefoot website, which I'm going to show you where to find it, so you can read up a little bit more if you'd like to. So on barefootcomputing.org. By the way, have you seen we've got some new resources out this week for the early years setting. So for younger pupils, 3 to 5, we've got our super space computational thinking resources, which are ace. So if you want to download those, there's a little bit of a plug for that. But if you go into the website and you log in and you go to well, it takes you to the home page and you go to My Learning and go to the Research, Pedagogy and Information Zone, you'll find this featured article, which we keep pinned at the top, all about PRIM. So PRIM was developed by Sue Sentence and supported by people like Jane Waite, who wrote a lot of the original Barefoot resources, as a approach, a kind of process to teaching computing, specifically the idea of how you introduce new concepts in computing and you take learners on a journey from them never having heard this concept before through to hopefully developing a confidence and competence in using it. So there are the 5 different stages. Oh, I can hear myself. All right, stopped again. 5 different stages in PRIM. And it just, the letters in the term PRIM are an acronym. It stands for predict, run, investigate, modify, and make. So essentially, you sort of work your way through, and we're going to have a bit of a go at this shortly, these 5 different stages. And they are pretty straightforward to explain. They are as they sound. So we start with predicting. So this kind of goes back to what we've done a lot of 2 weeks ago, where we were code reading. By reading code, we're sort of anticipating, predicting what it's going to do when run. So we start with getting learners to predict what some code will do. So if we're introducing a new concept, we will ensure that the code that we are showing them and asking them to predict includes that concept. And we get them to predict what it might do when it's run. And they record their predictions down. It could be by writing it or drawing it, whatever works for them. And then the next stage is they actually go onto the computer and run that code. So they run the code, they see if their prediction was correct. And often at that point, something happens which surprises them. The way we pitch this is that you kind of don't want their predictions to be always 100% right. You want to make it quite tricky. You want to surprise them in what happens when it runs so that you can move their learning on. You know, if they're predicting it exactly right, then you probably don't need to cover that concept. So chances are when it's run, something will happen that they can't really explain. Then you get them to start investigating the code. So to package that all up and do something new. So from everything that you've learned from the first 4 stages, some predicting, running, investigating and modifying, now go and use that, apply it, new context and make something with it. So those are the 5 different stages. in Prim, and we have some lovely Prim resources on Barefoot. What we did is we took one of our resources, Crystal Flowers, and we primmed it. So when we originally wrote our resources, this methodology wasn't around. So it's not something that we used extensively in all of our resources, but we've taken one and primmed it to show how it would fit into this model. And we occasionally hear from teachers that have taken other ones of our resources and applied the prim method. And so it's great to hear that feedback. So if you do that, please let us know. So let's have a bit of a go at this. So we're going to do some prediction first of all. This is not the one I want you to predict. I'm just going to do a little bit of modelling first of all, because predicting is so much more than guessing. You know, predictions are all about using prior experience to inform our predictions. So you might display a bit of code like this and model to pupils how you start to predict what it will do. And you do that by talking through line by line, really getting into the details. So, you know, the yellow block will start the program when clicked. Not sure what pen up is for. Doesn't matter. Erase all. Okay, so that might clear the stage and the sprite maybe. Then it's going to go to 100 and minus 100. So it's going to go to a place on the stage. Perhaps it's in the middle. Point in direction 0. No idea what this does. So you really want pupils to be talking through line by line of their code. And then they can start to kind of also group things within the code. So you can see the little annotations on the right hand side there. You know, I think all this gets everything ready at the top there, and then we've got the bottom part. So we're drawing a line, turning a right angle, drawing another line, but it's shorter than the first one. Then you can slowly predict that it might draw a rectangle. So it's not just a cursory look and a wonder and a guess. It's being really systematic in informing your predictions. So have a go at this. Here is a program. I hope it's coming across large enough for you to see. But I would like you to predict what the program will do and write your prediction into the chat. So it doesn't have to be really lengthy. You can, abbreviate a little bit, but just have a look through. You go through the process of really diving into the details to work out what's going on here, and then summarize that prediction and pop it into the chat. So I'm going to go this is quite a tricky one, this. I don't know whether you will get it correct or not, or partially correct or whatever, but I will stop talking for 2 or 3 minutes, 3 minutes, let you have a go and let you pop your predictions into the chat. And if anyone's got any questions in the meantime, just give me a shout. Okay, so let me come off of screen share now, like so, and stop sharing and have a look at some of the predictions that have come through. Okay, so drawing a hexagon and a decagon. Okay, that's an interesting one from Lynn. Thank you. Drawing a star or polygon with 2 colors. Drawing a hexagon and then not sure. Thank you. Thanks for your honesty there. Miss Wilkinson, you are technically correct, but I would perhaps quiz you for a bit more detail on what the style of the crystal flowers and the kind of movement between them. Miss Watson, drawing a hexagon and a decagon, different colors. Okay, super. Right, so Mr. Martin, clear the screen, set pen size and color, then draw a spirograph type shape. Yes, a spirograph. That was great, wasn't it? The pens, but they'd always jump out the thing and then ruin it for you. Right, so what I'd like you to do now is have a go at running this to find out if your prediction was correct. So I'm going to drop the link in the chat there. You can open that link up and you can run, and I'm going to go back to share my screen, so I'll do it as well. You can run it in Scratch. So hopefully you can all see this if you just drop the link in there, and then you can click the green flag and it will execute the code. So that is the output. I think Mrs. Wilkinson was probably closest with the crystal flower, which is a generic term for what we have got here. But in a bit more detail, it is a hexagon on the inside, and the hexagon then is drawn, and then the color of the pen is changed slightly, and the position of the pen is moved by about 40, well, exactly 40 steps, but turned more importantly to 30 degrees, and then it draws another hexagon. And it goes the whole way around until you have 360 degrees of hexagon that have been drawn, hexagons that have been drawn. And because you've got this slight change in color each time over the course of the whole program running, you get this kind of lovely rainbow effect. And for people that haven't seen those before, yeah, we call those the kind of crystal flowers. So it's the kind of thing we would do. So the predict stage, run it. Really important point here, model being curious and interested rather than disappointed. Were not fun. I don't know if anyone was disappointed there. It doesn't matter. I talk about this a lot with my pupils in science. Repetition are just a line and sound about what you understand. Then you run the experiment, and then you learn more as a result. And you learn more. You're going to progress more actually if your prediction was incorrect. So the next stage then would perhaps be twofold. First of all, you could do some of the investigate actually unplugged. So we talked a lot in week one about, you can do a lot of stuff in computing that's unplugged, not using technology, and you might have a sheet of questions printed out with the code, and this is exactly what we do in the Barefoot resource, where we say, okay, here is a number of questions now. Go and have a look at that code, go and investigate it. So question one here is, this program uses repetition. There are 2 repeats in the program. Can you find them and draw around them? Okay, and they might notice that actually one repeat is sat inside the other repeat. Do you know what these types of loops are called? We're going to refer to the loops as the outer loop and the inner loop. Can you label these on the program? So we can really do lots of work, just paper-based, unplugged, diving into the code. But what I'd like you to do is actually to do a bit of an investigate by going into that Scratch file that I've just posted for you. I think it's the same one as that, 709 it ends in, 709, yep. So see inside so you can see the code. That is the exact code that I have been showing on my screen here. And I'd like you to have a go at these investigation questions. So first of all, change the inner loop count value from 6 to 4, and then change the inner loop turn value from 60 to 90. And what do you think will happen the next time the program is run? So have a think of a prediction and run the code, and pop into the chat what you find happens then. And also have a go at this one, question 4. Change the value in the pen size to 1, run the program, what's different, and then change it to 5. So I'm going to go quiet again for 3 minutes for you to have a go at investigating the code in that program, changing those parameters and seeing what the outcome is. I don't know if anyone can maybe do a screenshot and drop that into the chat of their program, their crystal flower outcomes when they change, particularly for question 2 here. Let's see if we can get some screenshots in from question 2. Fantastic, super, thank you. So thank you to everyone who's shared that, and I can see the comments. Yeah, and Lynn's just posted them as well. So we've got the thicker and thinner lines there. Yeah, super. So That's great. So this stage is just all about diving into the code, altering parameters, giving them lots of questions to encourage them to explore the different concepts in that code, as you have been doing. Thank you. So then modify. Now, modify challenge. So when I first started working with Prim, I was sort of a little bit confused about the difference between modify and investigate, because I was thinking, well, you know, when we're investigating, we're just changing the code and modifying it. But the difference is that with modify, you're moving pupils on from investigating to making more purposeful changes. So this is our modify challenge in our Prim Crystal Flowers resource. So it says when the program below is run, a repeating pattern of hexagons is drawn. Modify the programs that the pattern is made from different shape, and each shape has different coloured sides. So you're actually starting to define the changes that you want the pupils to achieve, and then they go and, in this instance, actually identify and annotate the changes on the code that they are going to make those changes, and then they run them. So it's moving to more purposeful exploration. And then finally, it's the make. So here, it's a completely new project. Then create a picture by writing a program that uses colourful repeating patterns of regular shapes, including. So you're just giving them then the statement of the task who you want them to do, and they're going to apply everything they've learned in the first 4 stages of Prim to apply that into the make setting. So I hope that's clear. Please let me know in the chat or popping your hands up if you've got any questions on that one. But that is Prim. And I would really recommend having a quick read over the Barefoot article on it and downloading the Prim Crystal Flower resources and having a go with those. And then if you're looking, you know, whatever it is you're doing in your schools, I know lots of people that have joined this evening are doing the microbit course as well. You could look at how you can use Prim in whatever you're doing with your microbits in school. I'll be honest as well, sometimes I don't, you know, you don't necessarily have to go through the whole process. I might just pinch bits of it. So I like doing lots of prediction activities with my pupils, and then separately might do some investigating stuff. But it all kind of adds together as a sort of patchwork of developing their understanding. So that's number 1. 2 more to go this evening. So number 2, use, modify, create. I'm going to spend a little bit less time on this because actually we've already done quite a bit of this. So the basic premise of this is that it reduces anxiety when coding while supporting growth. And there's some nice research on this methodology, and you can do the Raspberry Pi Future Learning course called Programming Pedagogy in Secondary Schools. I know we're not secondary schools, we're working with younger pupils than that, but it's totally applicable, or everything that's covered is applicable, I would say. And the idea here is that we are transitioning from not mine to mine, and that process is what enables the reduction in anxiety. You know, I think I probably would have said in one of the previous weeks that when we're doing writing stuff or other language stuff, you know, it's quite intimidating for pupils to just always give them a completely blank piece of paper to do their writing on. We often scaffold things by giving them models of text, giving them sentence openers, which we know are of high quality. So we're replicating that here. So we start at the use stage, and at the use stage, pupils are given a program to explore. They're given prompts and questions provided to support that exploration. So it's kind of a bit like we're jumping at the investigate stage here. We've got a program that works, explore it, see what it does. Then you move on to the modify, okay? And as you move on to that modify, you are bridging the gap from not mine to mine. You're taking ownership of it. So once pupils have become comfortable with the program, they're encouraged to start changing it. So as they develop in confidence, then they're starting to tinker with it, getting it to do different things, repurposing it, etc. And then finally, as we transition to that full mine, was that Finding Nemo with all the seagulls? Mine. We work on programming challenges that use the skills nurtured in the use and modify stage, but they've now taken full ownership and they're creating their own programs. So, I mean, really, you can kind of map Prim over this, because the predicting and investigating and modifying is in that kind of non-mine, not mine stage, and then we take ownership as we move into the kind of make. But it just reiterates, really, for me, fundamentally, it's just not always about giving people as a blank scratch project and saying, right, off we go. It's providing some structure and support, as we did in Camels Come Dancing. So that's why I'm not going to spend too long on this one, because you've already experienced it. If you came along 2 weeks ago, we used it. We provided you with a dance program that already worked, and then you modified it and remixed it to match the algorithm which you had written for your dance routine. So again, this is one I use quite a lot in my teaching with my pupils. I have a number of kind of template program files that I've got that I use and roll out when I want pupils to start with something rather than starting with a blank scratch file. So that was a bit of a whistle-stop tour of use, modify, create. But that enables me to then get onto Parson's problems, which are probably my favorite pedagogical approach. Actually, I use these a lot. So what is a Parson's problem? Well, Parson's problem is a task that involves giving learners all the lines of code required to solve a problem, but with the lines jumbled up so they are not in the correct order. And again, we see this being used in other subjects. It's a long established approach to teaching reading and writing, for example. So the picture on the right there at the top is from the Oxford Reading Tree publishers of jumbled. So we're giving pupils the words, they need to work out the order. Now, the main benefit of Parson's problem is that we're focusing on the kind of code structure rather than the syntax. Now, what I mean by that is, rather than getting bogged down in the syntax of the right commands and whether the commands will fit together, we're saying we're more concerned with them understanding the overall concepts. You know, where do we need something to repeat? Where do we need to use a selection? Rather than, you know, is this right? Is this block right? Try a selection here. Or no, these are the bits, these are the commands that you will need, but you think about when you're turning that algorithm into a program where you are going to need them. I think it's really, really powerful, Parson's problems. It works particularly well in Scratch because the blocks fit together. They only fit together if they're going to work together, which kind of goes along with the Parson's problem ethos as well. You can occasionally put in distractors, blocks that they won't need, just a couple. I do occasionally do that just to increase the level of challenge. So let's have a go at a Parson's problem. We are going to use an example from one of our cyber security resources. So I'm going to stop talking, have a few glugs of tea. Assuming you didn't have a pair of bolt cutters and you had plenty of time on your hands, how would you work out the code for this lock? What's your algorithm? So please, can you pop into the chat your algorithm for cracking this lock, please? All right, Emma, would you mind coming on the microphone? Thank you for being first in there. Your prize is to come onto the microphone and talk me through your algorithm in a bit more detail. Are you there?
Yep.
Hello.
Right, so,
go on, go for it.
I didn't know how to explain it. So I would put them all to 0, 0, 0, 0.
Yep.
And then you said we've got all the time in the world, so I'm assuming I'm not aging, right? 0,
No.
0, 0, 0, and then I would change it to 0, 0, 0, 1, and then 0, 0, 2, and so on, and then like you would just go through. I can't remember how many combinations it is for a 4-digit lock, but yeah, you would just go through them all one by one if you had all the time.
I presume it's 10,000 because it's 9,999 plus 0, 0, 0, 0. Yeah. So yeah, fab. I mean, that's absolutely.
I didn't say it was efficient.
No, that's fine. But you'll see in a minute. Actually, in digital terms, it'll be very efficient. So, yeah, thank you for that.
It's the same idea. It was again starting 00, but I'd have one of the numbers in 4 loops repeating 10 times, but all nested inside each other. So the value goes 00, add 1 to that inner loop.
Yeah.
Of one of the digits, and that would run 10 times, go through from 0 to 9, then add 1 on, and then loop again. So it's 1. Yeah, it's a bit hard to think, but yes.
Yeah, no, I totally get it.
Yeah.
You're already sort of thinking about how you're going to implement this algorithm into like a coding language. So, so you basically talked about how you would implement apologies, I can't remember who previously spoke, but how their approach, you're thinking how you'd implement that using loops.
Yeah, and sort of nested inside each other, a bit like the decagon and the hexagon.
Yeah, because you've got the kind of the 4 different digits here. So you're going to do the first one, check all the way up to 9. If it doesn't open, you'll change the next one to 1 and check the first one all the way up to 9 again. So you're basically counting all the way up from 0000 to 10,000.
Yes.
9,999. Yeah, fantastic. You sound like, have you done this before? have you got a history in cracking?
Not in cracking locks, but a wee bit of coding from a distant past. Yes.
Yeah. Cool. Okay. Yes. So thank you for sharing that. And I mean, when I ask people this question, everyone arrives at the same algorithm. It's not particularly efficient. Can't imagine it would be particularly fun, but you can just work your way through. In fact, these locks only actually work because of the existence of time. They're not actually secure at all. They're only secure if you add in the concept of time. Now, this is what most people have said there. So you set the code to test 0000, see if the lock opens. If it doesn't open, increase the code to test by 1. Repeat steps 2 and 3 until the lock opens. Now, in the digital world, time is very different because we can do things very quickly, as we're about to explore. And there's something called a brute force hack. I don't know if anyone's heard of this before, but brute force hack is basically where you try all the possible combinations of things. And we're going to write a program in a second which does a brute force hack. Now, you might have noticed that phones now, previously you were allowed to have 4-digit PIN numbers. I think now they all stipulate that you have at least 6 digits. Because as I said before, when you're dealing with a physical lock like that and you're having to test each combination by hand, it takes a long time. It's effective. But in the digital world, we can do things a lot quicker than that. So we're going to have a go at a Parsons problem to actually implement this algorithm to hack a lock, to crack a lock. So I'm going to pop the project link. So there you go. If you just follow that, open it up, and you can start, just show you a couple of things. So you need to go see inside here. Okay. So we've got our algorithm here. We're going to set the code to test 000. Now, in our program here, we've got a number of commands, and we've got 2 buttons on our stage here. We can enter a secret number and find the secret number. So what you need to do is you click enter a secret number, and it says please enter a secret number, and I want you to enter a 4-digit secret number. Then what you're going to do is combine these blocks of code. This is our Parsons problem, so that when we click find the secret number, this code is actually going to implement this algorithm. So it's going to first of all set the code to test it test 0, 0, 0, 0. So I'm going to give you a clue here. I'm going to say that when the sprite is clicked, so when we click on this, the first thing that it's going to do is set the test number that it's testing to 0. Okay, because that's the first one we want to test. And then, oh, look, we've got a repeat here because we were talking about repeating, increasing the test number by 1. Right, I feel like I've given enough hints. So have a go now at combining these blocks of code to see if you can get this, when you click on this sprite here, it will actually do this brute force hack to find out what the secret number is. So I'm going to give you a little bit more time for this one because it's a little bit more involved. So it's 42 minutes past now. If I give you 4 minutes up until 46 and then I'll start talking again. So we want it to try and work out what when the number that it's testing is equal to the secret number, it finds the right number and then say what that number is. Okay, right. Let's ask the question then. Raise your hand either digitally, or you can come onto the camera and raise an analog hand if you want. Anyone feel that they are close with that Parsons problem of building a little program to? Oh, Emma, straight up there. Emma, where are you? Come on to the. Have you got your camera on there, Emma? Or can you put your camera on? Where are you?
Yeah, I can hold this up to the computer for a second. I haven't done it. I'm close, I think.
Okay, fab. Okay, great. Well, let's see if we can work together to get through. Right. I'm just going to pin you on here so that I can see. Okay, well, if you talk us through what you've done so far then.
Okay, so you put in the secret number, for the test number, when you click it and you want to repeat the whole thing until the test number equals the secret number.
Yep.
Start the test number at 0 and then change it by 1 every time. I'm just a bit I got someone came into my room, but I'm just a bit stuck with how you get it to keep going.
Yeah.
Up. But I'm just that's where I'm close, I think.
You are very close. You are very close indeed. So what I'm going to do, it's a little bit fuzzy looking at yours. So thank you for sharing that. What I'll do is I'll share, I'm still sharing my screen. I'm presuming that people, that's a real shame that people couldn't, maybe they could see yours because I'm sharing my screen, which is sharing my Teams. But let me now go back to mine and I'll talk you through it because I think I'm going to talk through a lot of what you've done, but maybe just slightly different order at the end here. You're right. What we want to do is when we click on this sprite, we want to set the test number to 0 and we want to keep repeating until the number that we're testing equals the secret number, and we'll know that that's happened because it will open the lock. And what do we want to do each time that is not the case? Well, we want to change the test number by 1. So we're going to repeat until the test number.
Oh, I think I got it.
You got it? Hey, super. Was that Emma again?
Yeah, sorry, that was a proper squeak. There.
That's it. Yeah. And have you clicked it to run it to see if it hacks it for you?
Yeah. So what it's doing is it's going up in ones very slowly. Like that.
Okay, right. So I think I might know why it's going up slowly because I think I saw that you had this say command within your loop. The only reason we've got that say command there is so that once the test number equals the secret number, so it's found the pin number, it will come out this loop and it will say the secret number is, whatever number you were testing last. Okay, so if I run this now, that's the Parsons problem completed, popped together. I can enter a secret number, do a 4-digit number like so, and if I hit find a secret number, in a fraction of a second, it tells me what that secret number was. Okay. Now, in this resource, just to share, just to say this, I love this resource because people have the idea. So, you know, we're really clear with people that any form of ethical hacking, cybersecurity, and it just shows how quickly computers can be used to hack things. You know, a 6-digit PIN number, which is what's required on a phone now. If I enter a 6-digit one, like so, and hit return and do find secret number, I mean, it took, what, less than a second then? You can also then use this little program to start to explain to pupils why longer passwords are more secure, because you only have to get up to sort of a 8-digit, and then all of a sudden things are taking quite a bit longer to hack, but still not massively. I think as I just rabbit on a little bit here, it'll eventually find the 8-digit PIN number that I've put in. I think it's coming up any second now. There we go. But it kind of grows exponentially. If you enter a 12-digit, that will be going for quite some time. This program can also then be used to explore with pupils why there are things such as you can only have 2 or 3 failed attempts, because that is a protection against a brute force hack where somebody is just trying to use as many different as just trying it over and over and over until they get the right thing. So nice little resource, this one. You can find this under our cyber resources, which have got their own page. Cyber. It's called You're the Cybersecurity Expert. Okay, so you can get that one there. But for the purposes of this evening, it was to demonstrate the idea of doing Parsons problems and providing the blocks of code that you need. You talk through the algorithm, provide the blocks of code, and pupils work out how they then fit together. So in the last couple of minutes that I've got, just to tell you about 2 resources, or rather one actually, because we've already touched on the Barefoot Computing Research Zone. But the other thing I would really recommend you get hold of a copy of is the Hello World Big Book of Computing Pedagogy. So Hello World's a great magazine published by Raspberry Pi, all about computing education, and they did a special issue a few years ago now, a couple of years ago, on computing pedagogy, and it's available as a PDF to download. It's got articles on Prim and everything we've talked about this evening, plus lots more, all completely free. The link is here. I'll drop it into the chat for you to finish, and let me pop it in there.